Alright, AGS1. We have reached the end of Mod 5, and today we're going to talk about 5.10, taken out of context. With this one, we're going to do a little bit of working backwards with story problems, like starting with a system of equations and then writing the story problem. But then after that, we're going to mainly just focus on solving some systems of equations and talk about a couple special cases. So, essential question of the day: what kinds of solutions can I get from a system of equations? First thing we're going to do is write a story context for this system of equations right here. So picture that, you were given a word problem and then you wrote this system of equations from the word problem, which is something we did with Carlos and Clarita a bunch in this unit. Now we're saying, like, if this was the system that somebody had written from a story problem, what would the story problem be? There's so many different answers to this, like, you can really get creative. Let's say, like, X is the number of Sour Patch Kids that you're gonna buy, and Y is the number of jelly beans. I guess I should say bags of Sour Patch Kids or bags of jelly beans. So, it could be something like Mr. Jolly bought 3 bags of Sour Patch Kids and 4 of jelly beans. And it was $29. And then we could say Ms. McNeely bought 6 bags of Sour Patch Kids and 2 bags of jelly beans, like jolly beans, jelly beans for $28. What are the prices of Sour Patch Kids and jelly beans? It's kind of awfully worded, but you get the idea. So, if Jolly bought 3 Sour Patch Kids and 4 jelly beans, and that was $29. McNeely bought 6 bags of Sour Patch Kids and 2 bags of jelly beans, and that was $28. This is the system you would set up to be able to solve the individual bag prices for Sour Patch Kids and jelly beans. So, let's actually solve it. I'm thinking, since it doesn't say I have to use a specific method, we can just do whatever we want. I don't think, like, graphing it or substitution is a good way to go about it. I'm thinking because this 3 and this 6 are very similar, that we can probably multiply the top equation by a -2 and then add the 2 equations together. And that would cancel out the 6 x's, or the x variables. So first thing I'm going to do is write it fresh down here so we can see it. 3x plus 4y is equal to 29, and 6x plus 2y is equal to 28. Okay, so I want the x variables to eliminate. I could have chosen the y variables, but I'm going to go for the x's. Because I want this coefficient and this coefficient to be opposites of each other, like the same number, but one positive and one negative, I'm going to have to multiply the entire top by a -2. When I do that, I will get, we'll put them over here. -6x minus 8y equals, what is that? Oh, 2 back from 60, -58. And then the bottom equation, I'm not going to change at all. I'm just going to copy paste it over here. Oops. So this is 6x plus 2y is equal to 28. Now, I see that the x's, if I add them together, will eliminate each other. That's like the key to elimination. So if I just add the two lines together, these go away, and we get negative 6y is equal to, I believe that's negative 30. Do you add those two together? Cool. So then, if you divide both sides by negative 6, you get y is equal to 5. Now that I've got y is equal to 5, I can plug that 5 back into either this equation or this equation. I'm probably going to go with the top equation because it's got, well, I guess it doesn't really matter. Actually, let's go bottom equation just to show that it does not matter. So if I rewrite the bottom equation as 6x plus 2 times 5, because that's the y that we just figured out, then this is one equation with one unknown, and we can solve for x. Subtract 10 from both sides. X is equal to 3. So, you guys, because we got an x and a y here, the way I want you guys to express that answer is as a coordinate. X, comma, y is your answer. So, our answer is 3, comma, 5. If I was taking a test or a quiz, and I had extra time, I would take that 3, 5 and plug it back into these original constraints to see if I get true equations out of them. So you can check your answers. Next one. Solve this. Doesn't say what method. You could go elimination or substitution. I'm thinking elimination because if I take this bottom one and multiply it by a negative 2, that could cancel out the x variables, because then there would be a positive 2 and a negative 2, and those two would cancel each other out. So, I'm going to leave the top equation, not going to touch it. And the bottom equation, I'm going to blast all of it with a negative 2. So we get negative 2x minus 2y is equal to negative 8. Now if I add the two equations together, these two will cancel out, which is great. So 2x and minus 2x is nothing. That's a 0. But wait a minute. 2y and negative 2y also cancels out. So on the left, I get 0. And over here, I get negative 10. Ruh-roh. What happened, you guys? Okay. This might happen from time to time, where you're trying to solve the system and both the x and the y go away. If that happens and you get something that is not true, like does 0 equal negative 10? No, it does not. This is false because 0 does not equal negative 10. So this is no solution whatsoever. What that would look like graphically, if you were to graph both of these things, they would be parallel lines that do not ever touch. They would have different y-intercepts, and they would go on forever without ever touching each other. So, no solution. Those are actually kind of fun because, like, once you get to the, like, everything eliminates, you're like, oh, it's less work. Let's try another one. It just says solve. It doesn't say to use any specific method. So I'm going to go elimination again. And my thought is to multiply the top by 3 because then the negative 3 and the positive 3 will cancel each other out. So I'm just going to make a note that I'm going to blast the top with a negative 3. So the top will become negative 3x plus 3y is equal to negative 12. And the bottom, oh no, I didn't want to do the top with a negative 3, sorry. I want to do it with a positive 3. Because then the, the coefficients here will be positive 3 and negative 3, opposites of each other. So, blast the top with a 3. So the top is 3x minus 3y is equal to 12. And the bottom, which I did not touch, I'm just going to move it over, is negative 3x plus 3y is equal to negative 12. Those look awfully similar, you guys. In fact, when I add them together, these cancel out, these cancel out, these cancel out, and we get 0 is equal to 0. This is another, what's going on? So, I just got finished saying if both the x and the y cancel each other out and you get a false statement, like 0 up here, it was 0 is equal to negative 10, which is not true. That's no solution. But here, 0 is equal to 0. This is true, that 0 is equal to 0. So, true. If this happens and you get a true statement, the answer is all real numbers. Or no, sorry, I'm steering you wrong. That's not what you should say. It's not all real numbers. That doesn't make sense because they're coordinates. But there is an infinite amount of coordinates that satisfy that the system of equations. So you just say infinite solutions. If you were to graph this and graph this, they would be the exact same line. They would be right on top of each other, always touching infinite amount of coordinates on them that satisfy the system. So another weird one, special case. Solve this. Doesn't say what method I have to use. Gosh, let's think. I think substitution is going to be too messy. I think it's going to involve fractions and stuff. But when I look at it, it's not super nice for elimination either, because I can't just multiply one of the equations and get it to like match up with the other one. So this is actually a rare case where you guys are going to have to manipulate both equations at the same time. Here's my thought. The first number that 3 and 4 have in common is 12. So we're going to multiply the top by 4. To make it a 12. Then we're going to multiply the bottom by a negative 3. Because that means when I do that, this coefficient will be a positive 12 and this coefficient will be a negative 12. So let's rewrite both of the equations. So this top one is 12x plus 8y is equal to 80. The bottom equation is negative 12x minus 15y is equal to negative 66. Now, when I add these two equations together, the positive 12 and the negative 12 cancel each other out, which is great. That's what I wanted. So these go away, and then 8 and negative 15 is negative 7. And then take 66 off of 80, and then it is 14. Hey, that's good news, because negative 7 goes into 14. You don't always have to get whole number solutions for these, but I think at this point, most of ours have been whole number solutions. I don't know if maybe we've had a couple where it was like a 5.5 or something. Okay, we got y equal to negative 2. So now I'm going to take this equation and rewrite it. But instead of y, I'll replace it with negative 2. So 3x minus 4 is equal to 20. 3x is equal to 24. Divide both sides by 3, and you get x is equal to 8. Which means our final solution is, in coordinate form, 8 comma negative 2. That's the x and the y. Next up. Solve the system with substitution. That means I can't do elimination. I have to do substitution. But, you guys, this substitution is really not that bad because, look, y is already by itself. Like, y is equal to 6x plus 4. So I'm just going to replace this y with 6x plus 4. So we get 6x plus 4 is equal to x minus 1. Subtract x from both sides. And we get 5x plus 4 is equal to negative 1. Subtract 4 from both sides. And we get 5x is equal to negative 5. And then x is equal to negative 1. Let's plug that back into this guy right here. And say y is equal to negative 1 minus 1. So y is equal to negative 2. Then we have both x and y. Let's throw it in coordinate form. There's our answer. Solve this with substitution. Now, I have to use substitution because it was part of the directions, But it's actually not super bad with substitution because this y is already isolated. So since that y is already isolated, we're going to take all of this and then put it right here. So we're going to substitute it into that y spot. So I'm going to rewrite the top equation, but instead of y, I'm going to replace it with 3x plus 1. And then you have one equation with one unknown, so you can solve it algebraically. Distribute that 2, and we get 6x plus 2. 6x and 4x are 10x. Subtract 2 from both sides. You get 10x is equal to negative 10. Divide both sides by 10, and you get x is equal to negative 1. Then I'm going to take this equation and replace the x with negative 1. So we get y is equal to 3 times negative 1 plus 1. So y is equal to negative 3 plus 1. So y is equal to negative 2. Final answer, negative 1, negative 2. All right, that was all the examples I wanted to do for you guys. So I thought since we have a quiz tomorrow, we'll do mini closure notes on 5.6 through 5.10. It was all about systems of equations. We started with Carlos and Clarita setting up systems of equations from word problems. So it was like a bunch of different things about him buying treats, different kinds of treats, different amounts of bags, equaling money. Know how to take a word problem and translate it into a system. Now, solving systems, we did do a little bit of graphing. Very, very little, I think one problem, but you can graph both and see where they cross. But then I would definitely estimate your solution and check it in the equations, because graphing can be deceiving. Please know the substitution method, where you get a variable by itself and substitute it into the other equation, and the elimination method, where you pick a variable and then you manipulate the equations to try to add them together and eliminate something. As we saw today, there are sometimes special cases of those systems, where if you get if the x and y go away and you get a number not equal to itself, then that is no solution. But if the x and the y go away and you get a number equal to itself, that is an infinite amount of solutions. Okay, you guys, good luck tomorrow. Happy studying.